Hello and welcome to this episode of Enough of the Science. I'm Joe.
And I'm Senan. What do we do here, Joe?
Well, basically, for anybody who's joining us for the first time, which may be you, listener, we talk about science topics, and Senan has the mind of a scientist, a great scientist. He keeps it in a jar under his bed, and he explains. We choose a topic every week, and he tries to explain it to my tiny mind. So what's the topic this week, Senan?
Hold on now, I'll just shoehorn in that brain that I have in the jar before we start talking about it. So, Joe, tell me, now I know the answer from you before I even ask this question is going to be no.
You should never ask a question unless you know the answer.
Do you ever experience that horrible feeling of being late for something?
No.
You don't. I know. I know you are the most punctual person on the planet.
No, I just have no conscience.
I, on the other hand, am very intimately familiar with the concept of feeling abysmal because you've been late for something you shouldn't have been late for. Anyway, the subject of this week's program is what the hell is wrong with my brain. No, the subject of this week's program is how
we don't have enough time for that, Sen. We don't have enough time.
How animals and plants keep track of time and how important it is.
This is obviously before everybody had a watch.
This is before the rabbits in the fields ran around with watches on their bushy tails, yeah.
Or they used to listen to the bells pealing from the village church at 6 p.m.
I have a vision of, you get out a sharp knife in the kitchen and you try and peel a bell. It must be damn hard.
I'm going to leave that in there. I shouldn't, but I'm going to leave that in there. So, on to today's topic.
Right, okay.
Time.
It's a fundamental feature of life on Earth. So many processes, it's critical. Like that, it's not just for humans, for animals, for plants. There are so many things that have to happen on time or the world just comes to an end as far as that creature is concerned. I mean, flowers need to flower at a certain time. Animals need to spawn at a certain time. Humans need to get up in the morning and go to work at a certain time.
People have to tune into this podcast at a certain time.
Yeah. And even bacteria are known to have... no, they don't. They can tune into this podcast whenever they want. And hopefully often as they want to.
Good. Well caught.
But
I just was checking if you were listening to me. That was all I was doing there.
Well, I don't listen most of the time, so you're lucky I picked up that one. Anyway, so there's so many different mechanisms because it has evolved in different animals for different reasons. There's like loads of different mechanisms for animals keep track of time. But let's just talk about us, well, mammals, but particularly us. Believe it or not, most of our cells, almost all of our cells, have their own little clock. So built into the cell, there's a couple of DNA proteins called clock and BMAL1. Lovely names, that. And
yeah, they weren't really kind of adventurous with the names when this is the clock. What does it do? What do you think?
Well, look, I suppose some of them are just wanted to have practical names rather than flowery ones. Anyway, these two proteins are responsible for the production of certain chemicals that, for want of a better description, build up in a reservoir in your cells. So for about 12 hours during the day, there's a little pipe that is producing these chemicals, and it's building up and building up and building up. And eventually, there's so much of the stuff has been produced after about 12 hours that the pipe gets blocked and no more new stuff is getting produced. And then it takes about another 12 hours for the stuff that's in the reservoir, the stuff that has been produced, to gradually degrade before the pipe is unblocked and it all starts all over again. So the total thing is a 24-hour cycle. And
the solar day.
Yeah, I mean, we've evolved on a planet where the day is 24 hours, and our biology has synchronized itself to that.
So this was present in all single-celled organisms.
Well, the particular mechanism I'm describing here is kind of unique to mammals, but most organisms down to the level of bacteria have something analogous to that, some way of tracking time, on a regular schedule. So, and it's all chemistry driven. So certain things are supposed to happen when that reservoir is full. Certain things are supposed to happen when that reservoir is empty. And some things even react to maybe when it's half full or whatever. So it's a chemical scheduler or chemical clock that's happening. Of course, there's a problem with that. If you've got millions of clocks, because we have millions of cells in our body, they're not all going to stay in synchronization if they're left to their own devices. They'll all be dancing to their own tune. The clocks will gradually go out of synchronization like any clock does. So there needs to be something to keep them all in sync, and that's where we come to the suprachiasmatic nucleus.
Charismatic. It's charismatic.
Chiasmatic. Anyway, so I'm just going to call it SCN from now on. Anyway, okay. It's a tiny, tiny part of our brain 20,000 neurons sounds like a lot. It's actually not, because there's billions of neurons in our brain. So it's a tiny part of our brain. It also uses our friend's clock and BML1 to keep track of time in those 20,000 neurons. But there's a couple of tricks it has up its sleeve. First of all, those neurons in that SCN area are all tightly aligned with each other. So they're talking to each other and making sure that all their clocks are on the same time.
Okay, so you basically have a big bunch of cells that are all aligned.
Yeah. Unlike all the other cells in your body, each cell doesn't really care too much what the clock in the neighbouring cell is doing, whereas these boys do. They keep an eye on what the neighbouring cells are doing. That's the first thing. The second is they have a very important resynchronization mechanism, because look at in the modern world, for example, if you fly to halfway around the world to Australia or somewhere, suddenly the day is happening when night used to happen. And all the processes in your body are happening literally at the opposite part of the day where they should be happening. The SCN is connected to the retina of your eye, and it receives signals of when it's bright and when it's dark. And it's actually able to gradually, over a period of days, that's why jet lag takes a few days to wear off, gradually over a period of days, it's able to resynchronize the clocks in your body to match the new reality of you're now in Australia.
So it takes a few days, and then suddenly you're aligned with...
Yeah, then when you come back again, you're all messed up at the end of your holiday. So yeah, and even it also, like, obviously in winter our days are a lot shorter, and summer they're a lot longer. At least they are in this part of the world. If you're near the equator, it's different.
I wonder, do people who live in the equator, like that's exactly 12 hours, are they slightly more aligned with their internal clocks, or their schedule?
They don't have the same seasonal variations that we probably experience.
Yeah.
You know, and I suppose when you think about it, when we were like hunter-gatherers living on the plains or whatever, you know, the time of year when there was more sunlight, there was also more food to be found. Whereas in the winter, when there was less sunlight, it was okay for us to be more sedentary. We didn't have to go out and be active finding food all the time, because there wasn't that much to be found. So yeah, that whole resynchronization mechanism had a good reason to evolve even before the age of jets.
It's not just there. Like all of this is not just there to cure jet lag. That's not why it's there.
It's just a handy. We're just convenient. We're piggybacking.
I wonder, did they ever do an experiment where they just kept someone in jet lag for a long, like just fly them to Australia, and they're jet lagged, and they're just getting over the jet lag, they're flying them straight back. Just to see how
long haul pilots and air stewards must experience that kind of thing.
Yeah.
I wonder, because there's definitely health implications of it being regularly disrupted. Like, they know from research done on shift workers who are working during the night that they are more prone to certain metabolic disorders, because typically, you know, your body is the processes inside your body are kind of run by hormones to a large extent. So hormones have to be released, certain ones at certain times, to synchronize with other things that are happening in your body. And a lot of that is being driven by your clock. There's the cellular clock. So, I mean, if people's hormones are being released at the wrong time, it's going to mess up the metabolism in their body. And it's certainly, like, in relation to the way food is absorbed, it's known that people on shift work are more likely to suffer from things like obesity or diabetes or high cholesterol. And there's even a link to cancer, because cancer is essentially DNA mutations, and that's what causes it. But your cells have an inbuilt DNA repair mechanism that runs or is supposed to run on a schedule to look for and repair DNA faults, and typically cancer only occurs where that repair mechanism has failed to identify a faulty piece of DNA and has allowed it to replicate. But if that DNA repair schedule is not correctly adhered to, there's a greater chance that some of these faulty genes will get through and cause
scheduled antivirus
cancer.
Is not working, and
yeah, well,
something
just to be
sneaks through.
Just to be complete nitpicky now, cancer, of course, is not a virus per se.
Okay.
But yeah. No, I get the analogy. Yeah. So it's serious stuff. It's important that the clocks are running right.
So for a good life, the more closely we can align with the 12-hour.
Yeah, so it seems,
that we are built to.
Yeah. Now, we are kind of flexible creatures. You know, obviously, people live in the north of Russia and north of Canada and north of Norway, where it's dark like all winter. and they manage to get by, although there is issues with depression and so on that they have to deal with more so there than they do here. But still, we are kind of flexible in that, you know, we there's a broad range of environmental conditions that we can still survive in. You know?
Yeah.
So that's all about the automatic stuff that's going on in our bodies that we don't have to think about. But then there's the whole other side of our conscious experience of time. You know, what I'm talking about is sometimes time seems to go very fast and sometimes it seems to go very slow.
And we let the listeners decide which way it's going today.
I'm sure it's going super fast because it goes fast when you're in what they call as a flow state, or when you're in the zone. You're deeply engaged in some task that requires a lot of concentration. It's a task that you get good satisfaction out of, so you know you're happy to be doing it. And time seems to pass really fast. A typical example is computer gaming. People can do hours-long sessions of computer gaming and not realize that much time has gone by at all. There's a really silly, complicated scientific name for it called transient hypofrontality. Transient just means it only happens for a short period of time. Hypo actually means low, although you might think it should be something hyper, which would be high. Hypo is low. What it means is that the part of your brain that normally consciously tracks how much time is passing, so you can have a fair idea how much is 5 minutes and how much is 15 minutes and so on.
Jack Reacher has spot on one of those. He can tell almost to the minute.
To the minute?
Well, yeah, pretty much. He wakes up and goes at 7:15.
Right.
He doesn't need to look at a watch.
Oh, that's a bit like, what's his name that was in Groundhog Day? Remember his clock went off every morning at the same time?
Yeah, that's not the same thing.
Well, look, it's related.
It's not really.
Give me a bit of latitude.
He's got a clock that's going off at the same time. Of course, he's going to know what time it is. No, this Jack Reacher has this bit that you were talking about in the brain that like kind of calculates time. And
the super charismatic nucleus.
No.
It was called.
This last thing that when we're in a flow state. And
Okay.
So that if you're conscious of time, but he's obviously got a very effective one.
Yeah, he must have. Yeah. He's got some use
for a
DNA.
Fictional character.
Quick, dissect him and see what he's made of. Anyway, the prefrontal cortex is the part of your brain that kind of consciously tracks how much time is going by, 5 minutes, 10 minutes, whatever it is. When you're in the zone, when you're deeply engaged in some task like we've just described, that actually goes quiet. It stops recording 5 minutes, 10 minutes, 15 minutes. And as a result, consciously, you literally don't feel time passing. And you know, after an hour, you stand up and you look at the clock and you think something wrong with that clock. It's an hour fast. So yeah, that's when you're deeply engaged. The opposite, of course, is when you're bored and time seems to crawl.
That never happens to me. I never get bored.
Usually when you and I are in conversation, I can see your eyes glazing over.
But that's because I'm thinking of something else, but I'm not bored.
Well,
I kind of wonder what I'm having for dinner, or
that's actually one of the characteristics of being bored is your mind starts to wander. And
now hold on a minute. That's a bit of an easy cop out. So I'm thinking of something else. Oh yeah, you're obviously bored, but I'm not bored. I'm not. Time isn't dragging. Okay. Maybe I just have an inability to be bored.
You don't have the boredom gene.
I don't have the boredom gene.
You know, they should do an experiment just to verify that. They should put you in prison and solitary confinement and just see how you get on.
Yeah.
We'd all be much happier to find that out.
Well,
in about 10 years from now.
Yeah, absolutely. I'll give that a go.
Anyway, you kind of your brain goes off wandering into lots of different topics, and because your brain is not busy paying attention to, say, some task that has you deeply engaged, it has more time for thinking about time passing. So you're kind of focusing more on the fact that time is passing slowly. So it's funny, it's all around psychology, but yet we have this real like flexible sense of how fast time is passing depending on what's going on around us.
So it's like in a waiting room, you can hear the tick of the clock.
Yeah.
And the tick doesn't seem to be going anywhere. Stuck in one position.
Yeah, you're there waiting for the talk. It's going to talk any minute now. It's going to talk. No,
it never does.
It doesn't.
It just stays with the tick.
And there is neurochemical, i.e. brain chemistry factors at play here as well. So dopamine is a well-known brain chemical that's involved in all kinds of stuff. It's essentially a messenger chemical. And part of its role is to help the different parts of your brain that are trying to keep time to stay in sync with each other, to communicate with each other in terms of what time it is and how much time has passed and so on. And people that have problems with the amount of dopamine also have problems with actually having a sense of how much time has passed. An extreme case is Parkinson's, which of course is a disease that is characterized by a low level of dopamine. And those people have really difficult problems knowing what time of day it is if they don't have a watch or a clock. To a lesser extent, some, like ADHD is one of those brain conditions that there's a lot of different flavors of it, or there's a spectrum of it. But some people have with ADHD have what's referred to as time blindness, where they can't adequately forecast how long it's going to take to get something done, or how soon they should start doing something that needs to be done by a certain time. So yeah, it's interesting how the chemistry of your brain is also playing into this sense of how time is passing.
So if you just took loads of dopamine, what would that do?
Well, I think there's happiness elements of it as well.
Okay. No, would you be super conscious of time? Would you just be like really, really able to just tell how long something was going to take?
Yeah.
Like,
one of the primary medicines for ADHD is a thing called Ritalin, and I think one of the effects of that is to boost the levels of dopamine in your brain. So that's interesting. Yeah, if somebody who already had normal dopamine levels took a lot of that, it'd be interesting to see what would happen.
Another experiment for next week. It's give me the Ritalin and solitary confinement. Let's see what happens.
At the same time, hopefully. So I guess that's enough about humans. Let's talk about some of the animals. And
yes.
So we'll just briefly touch on hibernation, because that's a kind of a different clock. That's a kind of a clock that certain things should happen at certain times of the year instead of at certain times of the day. And for mammals that hibernate, like bears and squirrels, it's a different part of the brain, the hypothalamus, that is kind of the conductor of the orchestra for all that hibernation activity. So it's keeping an eye on various cues, like the days getting shorter, the days getting colder. So we're talking about the autumn here, and maybe the supply of food getting lower and so on. And all those cues are kind of triggering its annual clock. It's a couple of stages actually involved in hibernation. It's really interesting. The animal needs loads of energy to survive through the winter when they're not actively foraging for food. They need to have energy stored, if you like, to keep them alive in that period. So a couple of weeks before they're due to go into hibernation, a hormone is released by the hypothalamus that actually gives them this incredible appetite, this unquenchable appetite. And
the munchies.
The munchies, exactly. And they go and they try and find as much food, and they eat absolutely everything they can find to build up some layers of fat, which will supply them with energy while they're asleep in the winter. So a few weeks go by, you've now got a tubby bear waddling around the place, and a different hormone is released into the system that induces what's known as torpor. That just means that all of the body's processes start slowing down. Everything slows down, and the amount of energy the body is using is slowing down. But the animal is also induced to become sleepy by this as well. And it eventually, I guess, causes the animal to consciously decide to dig a hole somewhere or seek somewhere to hide.
This torpor doesn't happen to humans when they get old, does it?
I don't know if that's there or not. Maybe it is, I don't know.
I mean, even I like sleeping more now than I did 20 years ago.
Yeah, actually, it's an interesting point. When you're younger, you tend to have more energy. So is there an element of that? Or is there just generally other processes in the body that make us more want to conserve energy as we get older? I'm not sure what that means. That's very interesting. We must research that one and do an episode on it.
Okay.
Aging. We'll have to do an aging
yeah.
episode. Yeah, we will.
You be the expert in that.
Seeing as between the two of us, we have more than a century.
You have more of that century than me.
Well, you can have some of it back if you like. Anyway, so that's hibernation, and also obviously the animal needs to wake up at the right time. The right time is usually spring when there's food around, but also maybe the right time could be when there's mating going to happen, because if you wake up at a time when there aren't other members of your species around wanting to mate with you, well, then you're not going to mate and produce babies, are you? So yeah, the actual waking up clock is also controlled by the hypothalamus in those animals. Let's go into the sea. David Attenborough was asked one time during an interview, which did he think was the most amazing animal? And without any hesitation, he said salmon. And they're like,
because they're delicious.
yeah, there is that. Yeah, there is that. He'd had enough of the beef. He was heading for the salmon. But yeah, no, what they do is pretty amazing. So they're born in a river, and they stay in the river until they grow to a juvenile fish size. and then they head out into the ocean. And they spend several years in the ocean, and they can literally swim halfway around the planet during that time.
In a shoal.
Not necessarily. They might be in a shoal, they might be singular, might not necessarily. And I think what probably happens is they shoal up with one group for a while, and then maybe they bump into some other group and they shoal off with them for a while. That's probably what happens. The point about this is, right, all of the salmon of a particular kind decide to come back to the river they were born in to spawn within a 2-week window. They arrive back within a 2-week window. Because they all need to be in the same place at the same time to reproduce, to mate. So for some kinds of
salmon, only 2 of them do.
Well, true enough, yeah. But if it's only 2, the chances of them finding each other is a bit tricky. But how do we know it's only 2? Maybe salmon have very exotic, sex lives. Who knows?
Look, the amount of information we have about salmon, I think we know that.
Anyway, some groups of salmon is 2 years, some groups of salmon is 3 years, some groups of salmon is 7 years. But the point is, all of the members of one group that are out of a particular river will arrive back at that river within a 2-week window.
So it's the one group that spawned together, headed off, and they all come back to...
Well, no, they didn't. They were born together.
They were born together
in that one river. And there's multiple mechanisms involved. Like there's two aspects to this. Obviously, there's the timing part, and then there's the navigation part. So we'll just talk about the timing first, because the navigation is pretty awesome too. There's a hormone in their thyroid gland that goes through annual cycles. So it's a bit like earlier on we were talking about that BMAL and clock proteins that we have that go through daily cycles of, rise to a certain level and then fall and then rise again at the same time the next day. Well, these have a hormone in their thyroid which is doing the same thing on an annual basis. So it's hitting a certain level once a year. And it's essentially what scientists call an oscillator, which is just tick tock, tick tock.
And once a year is just tick.
Yes, yeah, the salmon tick. And there's something in their system is counting the ticks. So it knows how many years have gone by. That's the first thing. Then there's a thing called DNA methylation. Which
of course there is.
Which is a kind of a counter of age. So gradually, from the time the animal is born, as they get older, the amount of methylation of the DNA, which just means that methyl molecules are getting attached onto the DNA, the amount of it is building up gradually, and when it hits a certain level, it triggers a mechanism that knows the animal has reached a certain age. So those are the two primary things that tell the animal when it's time to start heading home. But if you have a salmon that was born in a river in County Kerry in Ireland, and he's now cruising around off the coast of Canada somewhere, how in God's name is he going to find that river in Ireland that he has to get back to? I mean, there's no landmarks in the ocean. There's no signposts. How does he do that? We believe, although it's a theory, we haven't proved it, we believe that they're sensing the Earth's magnetic field, and they might even be able to see it in their vision, because there are a kind of cell, cryptochromes they're called, in the eyes of salmon, which engage in what's known as quantum entanglement. Now, we're going fairly far down the rabbit hole at this point.
Way down the salmon hole.
So anyway, this is something that Einstein theorized about but didn't really believe might happen. We now know it does happen. Now Einstein wasn't talking about salmon, by the way, but he called it spooky action at a distance. And essentially, subatomic particles, the building blocks of atoms, can have a property called spin. And it's possible to get two separate, say, electrons, for example, with the same spin entangled. In other words, they're keeping their spin synchronized with each other, even though they could be separated by light years. They could be millions of miles apart in space. If the spin of one changes, the spin of the other immediately changes to match. So essentially exceeding the speed of light. So that's why Einstein called it spooky action at a distance, because it was the only known thing or theorized thing that might actually go faster than the speed of light. Somehow these two particles were communicating with each other through some other mechanism that was able to exceed light speed. Anyway, that was a bit of a digression. That's not really the light speed.
It's like 4 years of college digression.
The light speed part isn't really important for the salmon. Essentially, these cells that are in, or chemicals that are in some of the cells of the salmon's eyes, when light hits them, it causes two electrons in two separate molecules to become entangled. So these two electrons have the same spin. Normally, these electrons would have a random decaying spin where it's changing and all over the place and no stability in it. Because these two are now synchronized, these two electrons in two separate molecules are now synchronized, it's stable, it stays that way. And for reasons I don't personally understand, it allows those cells to detect the Earth's magnetic field.
Okay, I just have one question.
Yeah.
How do they know this?
I don't know, but they know that robins do it. That's the big question. They know for sure robins do it. How they know robins do it, I don't know, but I think they've discovered the same kinds of cells that the robins have in the eyes of the salmon. I'd love to know how they figured it out for robins. But because these cells are in the salmon's eyes, that's why they think they might actually be able to see the Earth's magnetic field.
So the robins can see the Earth's
I don't know if
magnetic
it's in their eyes or if it's somewhere else in their brain or whatever. But
Okay,
robins
they can detect it.
They can detect, for navigation. Because a lot of people, certainly in this part of the world, you see robins in the winter and people assume that robins don't migrate to other countries. But actually some of them do. Some of them do go off and navigate their way down to warmer climates in Africa or wherever from here in Ireland.
Okay, so salmon are using the magnetic field of the Earth to find their way back to...
Yeah,
home.
it's like finding your way back to the eye of a needle from the other end of the country. You know, it's like incredible that they're able to do it. So that's salmon. We'll briefly talk about a plant that does something not quite as amazing as salmon, but still pretty amazing.
I suppose the cycles, like our cycles are getting bigger and bigger. So like we have a daily cycle in our cells, and then like the salmon is now 2,
3 or 7 years.
7
yeah,
years,
yeah.
like and the bears and squirrels are 1 year.
Yeah.
So now bamboo.
Yeah, we're talking about anywhere between 65 and 120 years. These guys have a clock that runs for. So we're talking about, say you've got two forests. All the bamboo of a particular species in forest A will all flower at the same time. All the bamboo of the same species in forest B will flower together but at a different time. So the first bunch in forest A might go in January and the second lads might go in March or something like that, right? Except we're talking about years here, not months. So the bamboo plant flowers once and then it dies. But these guys all together know, like 65, 80, 90 years after they initially were burst out of their seeds and became new plants, they suddenly have somehow figured out it's time to flower. But the really weird part is, if I take a bunch of the bamboo from forest A and I bring them to another country on the other side of the world, and maybe 30 years goes by until the clock has finally reached the time for them to flower, they will still flower at the same time as the ones in forest A that they were with.
This is quantum entanglement.
We don't know.
You take the bamboo and you go like light years to a different planet, flowers at the same time.
You could be onto something there, Joe. We could get a Nobel Prize out of this episode.
Here we go.
You just never know. Hopefully some scientist who understands this stuff will actually follow it up and get a grant for the research. So yeah, it's pretty cool what they can do.
Well, it's just the clocks. I mean, the fact that there is an internal mechanism that can keep track of solar years and days that like is inbuilt in the DNA and
goes on for 80 years or more. Yeah. It's phenomenal that it can trigger so accurately in separate plants in separate places. So we're nearly running out of time here, but I'm just going to very briefly mention some other interesting animals. Cicadas, who are like, those old movies where the scenes at night time in the jungle, you'd hear in the background all these cricket-like noises. They're actually cicadas.
Are you sure that's how it's pronounced? Cicadas,
I have no idea. It could be
cicadas.
Cicadas.
Let's call them
cicadas. Yeah.
Cicadas.
So periodical cicadas are a particular type of cicada that. Like most insects, they have a larva grub stage in the first part of their life, and then later they change into a flying insect. The larva stage is lived underground by them, and some are on a 13-year cycle, some are on a 17-year cycle. But all the ones in one place together, after 13 or 17 years spent underground, will all at the same time emerge and become flying insects, so they can all mate with each other. How do they keep track of that? Because underground they don't have any light.
No watches, no TV.
No watches, no TV. They can't hear the pealing of the bells, one assumes. But somehow they are able to keep track. Now, there's a theory that it might be due to the fluid coming out of tree roots. So these guys are living in the ground around tree roots, and certain chemicals are exuded by tree roots into the soil. And the nature of those chemicals changes depending on the time of year. So the stuff produced by the trees in the winter is different from the stuff produced by the trees in the summer. They think that these creatures, these bugs, these cicadas in the ground might be able to sense those changes and count how many times, a bit like the rings on a tree, count how many times the fluid has gone through a cycle of changes.
And 13 times or 17
Yeah.
times. Is it really odd, the numbers though? Like you could understand if it was like, okay, someone would do 4 years and someone do 8 years.
So those are both
someone
prime
do 12.
numbers.
Yeah.
Those are both prime numbers. And it might allow them to skip over other, say, predators that are on a schedule that is maybe not prime numbers. It might be.
Yeah.
Who knows?
They just picked awkward numbers to be on their own.
Yeah. So, look, we could go on talking about the amazing antics of animals and their clocks for the rest of the day, but I think probably we have now gotten our users out of the flow state and into
Into the what is this about state.
Yeah. So we're definitely thoroughly and absolutely out of time here. So it's goodbye from me until the next time.
Good luck from me, and enough with the science. Hope you can join us for the next episode. Take it easy.